Hello and welcome to this latest video demonstration of Icon Science's RokDoc software. Today we'll be taking a look at the Reservoir Characterization module with particular focus on the Seismic Data Conditioning or SDC and Seismic Inversion tools provided as an add-on to this module. In this case study we're looking at data from a discovered oil field, with the aim being to refine our understanding of reservoir architecture and the petrophysical properties between the wells using seismic amplitudes, with the ultimate aim of optimizing production from this field. The Reservoir Characterization module is the ideal space to perform these types of analyses, and seismic inversion is a key step in the seismic reservoir characterization workflow. Please see the accompanying video for a demonstration of the wider capabilities of the Reservoir Characterization module. The sessions themselves are recipe-based and can be viewed on multiple section, map or 3D views simultaneously. Here we have an arbitrary line displayed in two views, but any inline, crossline or arbitrary line can be displayed. An interactive map viewer is provided, as well as a 3D viewer where any data from the session can be displayed, including well data, horizon data or volume data. Any interactive property defined in the session can also be viewed in 3D. In this demonstration, we will aim to take the seismic amplitude data, optimize it for QI workflows, perform seismic inversion, and ultimately generate estimates of phase sheet distributions across the volume, as well as petrophysical properties within those phase sheets. The seismic data conditioning tools allow the optimization of seismic data for use in quantitative interpretation workflows. An SDC workflow is provided. This is a recipe-based workflow where a number of conditioning steps can be chained together with the results of each step computed on the fly and fed automatically into preceding steps. Furthermore, advanced SDC tools are also provided. The add-on provides access to multiple seismic inversion techniques. These are different methods of generating elastic properties from seismic amplitude data. We will review the colored inversion tool, a robust technique for generating relative and absolute attributes from single stack data, as well as a model-based approach. For this, we will focus on the Simultaneous method, where multiple angle stack seismic volumes are inverted for elastic impedances. Icon Science also provide a proprietary, rock physics-infused, phase sheet-aware Bayesian inversion method, RokDoc JiFi. Please see the accompanying video for more information on this award-winning reservoir characterization technology. The SDC workflow is shown here. Any number of workflows can be defined, and conditioning steps are added to the interactive list. The SDC workflow is applied to a selected set of pre- or partial stack data. A number of different steps are available and can be added to the workflow. These can be reorganized and reshuffled at will within the list. For illustration, we will apply a residual move-out correction step and review the impact on the implied AVO via the calculation of AVO intercept and gradient products, pre- and post-alignment. The alignment itself is a first-order Taylor series expansion technique for estimating a time shift between two traces. The parameters for each step in the flow can be specified, and here we need to specify the pilot trace, window length, and time gate. A smoothing can also optionally be applied to the time shifts before they are applied. Once calculate is clicked, the recipe is run along the displayed data only. A gather QC view is provided, and any step in the workflow can be compared. Here we see the angle stacks before and after alignment at one of the well locations. It is important in this case to review the impact of the alignment on the AVO at each sample. Once the workflow has been calculated, an interactive recipe is stored in the data tree. This can be run on any displayed line or map, and the recipe can be edited or updated at any time. The outputs from any step in the workflow are stored in this recipe and can be calculated on the fly. The module also allows the rapid QC of data along any line or as map extractions. For example, here a zoomed section is shown around one of the wells. At each CDP, the angle stack traces are displayed. We can then display the angle stacks before and after any SDC process. And again, the recipe can be calculated on any selected line, and comparisons can be made between multiple lines. Attributes are another key method of assessing the impact of SDC on the seismic responses. A variety of pre- and post-stack attributes can be calculated. Specifically for trace alignment, we can extract AVO responses along any seismic interpretation. Any data can be selected when defining the attribute. This includes recipe outputs such as those generated by our SDC workflow. The blue here is the AVO extracted at the top reservoir from the data pre-SDC, and the red post-SDC. Another attribute that is useful for understanding the impact of trace alignment is cross-correlation. We can generate a cross-correlation between the near and near-mid stack traces over the interval of interest prior to alignment. The attribute can be calculated over any selected window. A shift is also estimated that will allow the maximum cross-correlation between two traces. The cross-correlation can be mapped out across the volume using the map viewer, and the cross-correlation between these two traces can be reviewed. The same attribute can be made after alignment, and an improvement in the cross-correlation can be seen. The cross-correlation is calculated from the trace alignment recipe. The alignment is performed on the fly for use in the attribute calculation, and no aligned volumes have been generated at this stage. Any updates to the alignment step would be automatically reflected in this attribute and therefore in the map. As a final illustration of the SDC workflow, and another assessment of the effect of the trace alignment step on the AVO, intercept and gradient products are added to the SDC list, before and after the alignment step. In the case of the intercept and gradient calculation, multiple fit options are provided. And as can be seen, the same process can be added multiple times to the same workflow, and the steps can be reordered interactively. The two quantities can be compared along the section views. The intercept product shows little change after alignment, but the AVO gradient product is visually cleaner in the geologically quiet overburden, with brighter gradient responses seen over the reservoir interval. Any or all of the steps in the SDC workflow can be realized as volumes and exported to SegWire at any time. Multiple properties can be added to a queue for export. Advanced tools are also provided by the Advanced SDC license. These include structurally oriented filtering, frequency slice filtering, and gradient stabilization. Next, we'll take a look at the frequency slice filtering tool. This tool is designed to remove noise from the low frequency part of the seismic amplitude spectrum. This is achieved by applying a frequency-dependent filter to discrete frequency slices, based on the fact that the spatial resolution is partially frequency-dependent, and therefore the lowest frequencies are oversampled by the fixed, close-spaced seismic grid. A time window is specified, and a filter shape can be defined based on the size of the first Fresnel zone, or arbitrarily per max and min frequency. The filter can also be asymmetrical if required. The outputs include the filtered volume, the residual and high-cut filtered QC products that only show the data that has been filtered. These results are stored as interactive, editable recipes and can be realized and exported at any time. The effect of the filtering is visually subtle as we are targeting the low frequencies, so it is more informative to look at the residual. We look for steeply dipping noise and not coherent reflectors, which could indicate that the filtering has been applied too harshly. The high-cut quantities allow the filtered frequencies to be reviewed. Any of the recipes can be calculated along any selected data. For example, a horizon-following slice is extracted through the residual to understand the effect of the conditioning across the volume. The residual from the conditioning step is performed on the fly for the data selected in this map view. Next, we will review some of the seismic inversion methods provided by the SDC and Inversion add-on. First, we will look at the coloured inversion tool. This is a convolutional technique where estimates of relative impedance are generated from seismic traces. An operator is designed that applies a spectral shaping and -90-degree phase rotation to the data. The spectral shaping is performed with reference to a specified frequency range and the earth impedance spectrum for the particular attribute. The input seismic is assumed zero phase, and there must be consistency between the attribute and seismic, for example, acoustic impedance and AVO intercept. The earth impedance spectrum can be calculated based on the well-logged derived response. a multi-well log selector is provided for ease of selecting logs from multiple wells. The seismic spectrum can be extracted around the wells or from a selection of traces across the volume. The frequencies over which to perform the shaping are also specified. Once the operator has been calculated, it is displayed in time and as an amplitude and phase spectrum. Any parameters can be adjusted and the operator can be updated. Optionally, low frequency information can be blended with the relative impedance result to generate absolute impedances. The low frequencies can come from any source preferred by the geoscientist. Here we will use interpolated well data. The inversion should be run at the wells to assess the match between seismically derived impedances and log-derived impedances, and this can be done in a multi-well sense. We will also apply a high-cut and bandpass filter for the comparison. In this multi-well view, we now see the seismically derived impedances in red and the log-derived impedances in black for the absolute and relative cases. We can also review the seismic, earth, inversion and operator amplitude spectra for QC. Once set up, a recipe is stored and inversion can be run interactively on any line or map without realizing the entire volume on disk. Here, a horizon following slice through the relative AI is displayed. The inversion is being run interactively on the data selected in the map only. Next, we will review the model-based inversion methods, focusing on the simultaneous inversion. We invert multiple partial angle stacks for estimates of elastic impedances. This is done using a reflectivity equation, low-frequency model, and wavelets per stack. Any partial angle stack data can be inverted, and this includes output recipes from the STC workflow. The inversion can be applied either in PP mode or in PP-PS mode, where P to S reflection data is included in the inversion. The reflectivity equation selected here is used in the forward model and determines the elastic properties that the inversion will generate from the seismic data. This inversion will generate estimates of impedances from partial angle stack seismic data based on an objective function. The inversion uses wavelets to make a connection between the reflectivities generated by the inversion and the seismic data. These wavelets can be angle dependent, two-way time varying, and laterally varying if required. This type of inversion also requires a model to provide the low frequency information, and this again can come from any input volume or recipe. A scaling analysis can optionally be performed before the inversion to ensure the relative offset scaling is correctly captured. The elastic properties generated by the inversion need to be constrained using relationships based on log data. The relationships are defined based on the reflectivity equation selected, and here we define trends between AI, SI, and AI rho B. The frequency content of the background model can be specified, as can the model weight, which controls how easily the inversion can wander from the low frequency model. Additionally, impedance factors are provided that control how rigorously the elastic property trends are adhered to. The stack weights allow the influence of each angle stack on the inversion to be controlled. Many derivatives can be generated from the inversion and stored within the recipe. It is also important to look at QC properties such as the residual and relative impedances from the inversion. A direct matrix inversion is implemented, allowing rapid performance on any displayed section or map. QC spectra are displayed, showing the amplitude spectra of the angle stacks, inversion, synthetic, and residual. As with any process, an interactive recipe is saved to the data tree, and this includes the elastic impedances inverted, the inversion synthetic, and the residual. The low frequency model and any selected derivatives are also stored here. The inversion should be run at the wells for QC, and other QC tools are provided, including cross-plots of log and seismically derived impedances and matched statistics. A well view is displayed showing a comparison between the logs at each well and the inverted impedances, both absolute and relative. The low frequency model is displayed in blue, the log data in black, and the inversion profile in red. A multi-well panel is displayed showing a comparison of the absolute impedances relative impedances, and the seismic data synthetic from the inversion and the residual. This panel can be easily configured so that the performance of the inversion at the well can be interrogated. The crossplots show comparisons for all inverted impedances, both relative and absolute. The inversion can be run on any displayed data, and here we can view the AI in the upper section on the left and the VP/VS ratio in the lower section on the left. Just as with recipe outputs from any workflow, such as the SDC workflow, the inversion recipe outputs can be fed into the preceding workflows such as Bayesian classification. At this stage, the inversion has not been realized or exported as a volume. This means that I can edit the parameters of any step and the end result will update to reflect the changes. For example, I could change any of the inversion parameters and the inversion result would update, and therefore the Bayesian classification result would change. The Bayesian classification recipe, which uses outputs from the inversion recipe, is now run along a horizon-following slice. As this is being run, both processes, inversion and classification, are being performed on the fly. The same is true of the 3D view in the bottom right corner. Next, the inputs to the inversion will be updated. Here I select the outputs from the SDC workflow defined earlier. We now have a 3-step interactive recipe chain. The impact of the trace alignment performed in the SDC workflow can easily be assessed on the inversion results either at the well or along the section. In the bottom left section, we can see the impact of the trace alignment step on the VP/VS ratio produced by the inversion. If I update the SDC workflow parameters, perhaps changing the alignment time gate, the effect cascades through the chained recipes. First, the impact on the inversion can be assessed, and then the impact on the Bayesian classification can be mapped out. Again, as the map is generated, the processes are being performed on the fly based on each recipe: SDC into inversion, inversion into classification. As a final update to the inversion, I will include all the SDC steps performed earlier, these being alignment and filtering. The last step in a seismic reservoir characterization workflow might be the prediction of porosity from inverted impedances. This is best done in a per facies manner, so that the correct rock physics transforms can be used across the volume. A per facies inverse rock physics modeling function is provided in the reservoir characterization module. The result shown in the bottom left is now the product of 4 chained recipes: seismic data conditioning, seismic inversion, Bayesian classification, and per facies porosity prediction using rock physics models. A final update of the Bayesian classification on the map is performed so the uplift of the conditioning steps can be further visualized, and as can be seen, the result is now more stable across the map. Profiles at the well locations can be extracted from any interactive recipe within the session. Dynamic logs automatically update to reflect changes made to any of the recipes that go into generating that log. So for example, if I changed any of the seismic data conditioning parameters or any of the inversion parameters, the resulting porosity prediction as a log at the wells would update. In this view, the porosity profiles predicted from seismic are extracted as dynamic logs. The panel here shows a good match between seismically derived porosity in red and log-derived porosity in black. The porosity prediction is dependent on the seismic data conditioning, seismic inversion, Bayesian classification, and reverse rock physics modeling per facies, and all of these steps have been performed as interactive recipes with no volumes generated on disk at any stage. The aim of this demonstration has been to highlight not only the advanced functions provided by the RokDoc reservoir characterization module, but also to illustrate the interactive, recipe-based nature of the tool. This allows seemingly complex processes to be performed both easily and interactively, and results generated in short timeframes. For more information on any of the functionality demonstrated here, please contact info@iconscience.com or visit our website at www.iconscience.com. Thank you for listening.